So good afternoon, everybody. A warm north of England here. So yeah, hopefully
warm Birmingham here as well. Yeah,
warm Birmingham as well. So hopefully we're not keeping you all too far away from the sun, and or we're helping you hide from it. One of the two. Welcome to the third of our seminars.
Finally,
of our little mod sim seminars. We're going to be looking today at this, but first off, who are we?
Yeah, so welcome along. I'm Barry Chatham. I've recently joined Technia, so I've been here, 3 months now, I think, Andy?
Yeah.
Yeah, that's flown past, isn't it?
It has.
Again, my role before that, I've been in industry and product design for years, been in the SolidWorks channel for the last sort of 10 to 15 years. So again, I know the pain that you guys have been going through. We've gone this mod sim approach, and something's very close to my heart, being able to test stuff as part of the design before you even commit to spend any money. So, I feel your pain. Obviously, when I saw this, this topic, I thought, I want to get involved with this. And so hopefully it's going to be beneficial. If you watch the other two, if not, obviously they're going to be on the website. Make sure you watch the first two that we had in the series. They are very informative and kind of hopefully answer some questions or give you some thoughts towards doing stuff slightly differently.
Yeah, and I'm Andrew Steele, the Territory Sales Executive for SolidWorks and 3DEXPERIENCE works at Technia. Very similar background to Barry. We've known each other 20 plus years, from going to university together and working in similar industries ever since. And yeah, like Barry, I've felt these pains. I've lived the world of designing and hoping that the product that you design performs well in the field. And if these tools had been available back then in the late 90s, well, I guess they were starting to be. I remember my first product design company invested in Cosmos Works, but we didn't have a clue how to use it back then. And hopefully what we've been talking about in these last few videos has been valuable and given you, like Barry says, again, there's some thought points of what ModSim could do to help you and your business.
I think it's one of the things, Andy, you do it day in, day out and stuff. It's not until you sit back and go, are we doing this right? Is it the right approach to take as we've always done?
Yeah, and it needs it. It's not that at the minute, and when it gets to the point where it's just a matter of fact that you start doing this simulation, and that's where we need to get to. That, like I've mentioned it so many times, that I think designers are scared of testing because they don't want to fail. But the sooner we test, the sooner we fail, and the less impact it has on the final product. So we just need to stop being scared of testing, embrace it, because in the end it makes for a better product. Like coming all the way back to the taste test, if we just cook a meal, put it on the plate and hope it tastes nice, it could well do. But if we just test it and taste it as we're going, that confidence grows so much quicker, and we end up with a meal or a product that it performs so much better.
Yeah. So again, guys, just going to reviewing where we've been. We've done 2 seminars. The first one was looking at a huge big assembly, this kind of the resin driller machine. So again, we looked at a static load on the arm there on the boom, and be able to apply different kind of machinery to the end of that. As part of the concurrent in the design, test the assembly to make sure under certain loads it's going to pass first time to meet the market. First time, right? That's the main thing. So it's we know it's going to work. It's not going to fail. The second one, we looked at the rail industry and the rubber bushing, looked at non-linear analysis of the rubber bushing in there.
Yeah, and we also considered the manufacturing process, so we understood how that manufacturing process impacted on the performance of the final product.
Yeah, so the third one today, the third in the series, is kind of looking at this WaterJet cutter. We're trying to work out, as we can design the thing. It may even be we've got the guy in the factory who's done these for years, and we use a lot of his opinions and his thoughts and stuff to then run through this and double check before we even commit. As with all of these things, check it, test it beforehand before we press the button. So in this one, because we've got a motor in the machine and a pump in the machine, running very sort of high velocity water jet through that machine, could be cutting steel, it could be cutting titanium, I don't know. But at the end of the day, you've got to cover the marketplace to make sure that it's going to cut the steel. It's not going to fail. It's not going to bend itself out of shape and rip itself a bit. So being able to test early, hopefully get the answer where we need to be.
So like we have on all the previous videos, we're going to be using the 3DEXPERIENCE Works platform for this. We've started to see more and more of it as the slides have come on, and all of these lines that we've got here, these bullet points, really stand true. It's fully integrated and it's design centric, and the big one in here is that it's on cloud, scalable and collaborative. So you may start with a small design company or a design department with 1 or 2 design engineers, but then the 3DEXPERIENCE Works platform can propagate out to every department within the organization, be that QA, be that manufacturing, be it procurement. All of those business customers within the greater organization can have their input, even marketing. That always make things want us to make things that just really aren't quite possible for a price that can't be achieved. But every part of the organization can feel the influence of a 3DEXPERIENCE and see the gains from it. And like last time, we're using SolidWorks as the CAD platform, but it could be CATIA. In today's seminar, we're going to spend much more time inside Simulia than we are the CAD packages. I think we've demonstrated on a few occasions how we can bounce backwards and forwards and how they're working on the same data sets. So we're going to concentrate much more in Simulia today.
So as you can see, you're going to be looking at this WaterJet cutter here. As you can see on the image there, it's been made in America. Like with all Americans, that they're very proud of it. You know, the fact they've got that stamp in there, 1.5 foot kind of along there, that logo. They want to make sure when that machine goes up to a customer being shipped from their factory, it's off the trailer, plugged in, wired in, and it works first time. They don't have failures. The last thing that they want is their customers saying, your machine's rubbish, it breaks down, it falls apart, whatever it may be. So for these guys, it's been critical that they can test this under a number of different scenarios, whether it be, as I said before, again, I'm talking out just from air here. I'm assuming there's going to be different scenarios based on if you're cutting steel or if you're cutting titanium. So for these guys, they want to make sure that it does it first time, every time, and they then become market leaders. As we've said through every video, and I think you're right, Andy, there in the fact that it's all about being, the market leader, first to market, with 0 failures, and confident that the machine's going to work every time.
Yep. And then we're going to be looking at this assembly within that. So in exactly the same way as we did with the resin and with the bushing, we're going to first need to get this data up into the cloud. We've modeled this on SolidWorks on our desktop, and currently I'm the only person who's got access to it, so I need to share that with Barry or whoever my structural engineer is. So again, we'll whiz through this because you've seen it several times by now. We select our data that's been stored on our desktop. We can see that we've got lots of orange disk icons there, which means that it's not on the platform yet. We request to push it up to the platform, and away it goes. Takes a second or two, or a minute or two. What are we on? Couple of minutes, it looks like this one takes in real time to get up there.
We need to do some hands-on, Andy. Get to see the customers. Sit with them with a PC and actually do this live with them. Let them drive the system so they can see how quick and how fast that is. To then, play parts of the role. Whether I'll be a marketing person or I'll be a sales director saying, I want one of these. I want it tomorrow for half the price. Then going through this process, that we're going through today. So I think that's something we need to push that internally.
Yeah, and we're hoping that in the next coming weeks and months that we'll be running those on a regular basis. So if you people have got experience of SolidWorks or Simulia and want to see how that is integrated in the platform, then keep an eye out on the website for events that are going to be coming up in the future. So just skipping back a little bit there, you can see that we've now got a load of green ticks, which show us that it's moved up to the platform. Now we're going to open up the Simulia native app on our desktop directly from within the 3DEXPERIENCE SolidWorks. Give it a name.
And just stop you. Can I pause you there, Andy?
Of course.
So I'm assuming, you know, we can work with the customers to then look at whether you've got a name. We're giving it a name, yeah. It may be a part number. It may be a naming convention, yeah.
Yep.
So we can make sure, you know, I know what it's like to have the QA manager giving something the wrong name, or even, you know, trying to find a back plate, side panel. Companies don't like that or allow you to do that, but we can work with you to make sure, you know, you're giving it a name there, the OMAX. It follows the right naming convention, you know, when you put it in there and you start working with it, yeah.
Yeah, so we got a team of PLM engineers who live and breathe the 3DEXPERIENCE platform. We've been implementing it for many years now. But the PLM, the 3DEXPERIENCE platform is amazing, but it is just a tool. So our goal is to tailor it to fit with the way you work. If we all of a sudden come in and totally rip up what it is you're doing, then that's not going to necessarily be embraced by your users. So there's a bit of a balancing act. It's out of the box, but there are tweaks that we can make to make sure that it suits you. And yeah, exactly like you say, Barry, it's we can help make sure that all of those QA workbooks and workflows are all adhered to. So the first study that we're going to create is just a structural one.
So what are you testing for here?
So what we're going to do first off is just literally build this as a subassembly and make sure it doesn't fall apart, to be oversimplistic with it. We've got a whole host of different components that are all going to come together, and we want to make sure that they're all up to spec, and that well, exactly like I say, that this is a precision bit of kit, and we want to make sure that that precision isn't affected by the extrusion being too thin, and it ends up with a bit of flex, or or the other way around, that we're making things so thick and heavy that it costs us a fortune to ship it. So it's all of those things come together, so we get that nice balance between not over designing something and not under designing it either. So we're going to run a series of simulations on this. And first off, we're going to create the mesh as we've done with all the other ones. So that a lot of these steps are recognizable to all of you from previous videos. And then we're going to do that static analysis Barry's just mentioned. Does this thing flex? We've got a lot of levers going on here. Where does this move just by putting it together? Then we're going to do a low frequency analysis, and it considers the pump that's in the bottom. We'll touch on that in a little bit. And then we've got a high frequency analysis, which looks at the force of the water coming out of the nozzle, which actually does the cutting. So we'll see all of that being generated, and then we'll be able to look at the results and see what they mean for us. There we go. So the first thing we're going to do is get those meshes done. So we're going to switch into the assembly view. So this is hiding all of our analysis steps and what have you. We're not worried about that at the moment. We're just wanting to make sure that we've got the geometry in a good state to be able to work with it, and we understand what is going to be doing what. So we want to apply mesh, and with this we've got components various sizes, and where the forces may be distributed within them in different ways. So we're going to apply different mesh rules to different parts. So the arm and the gantry may need one type of mesh, and the other parts others. So Here we've got a component which has already got a mesh that's been applied to it, and we don't want to recreate the mesh. So we're just going to whiz through all of the assembly, find everything that's already had a mesh applied to it, and just say, oh, don't mesh it again. And there we go. We really quickly whizzed through that. And now we say, right, the rest of it, put that mesh on it. We tell it that we want the mesh size to be, I think it's 20 millimeters on this one. There we go. Lots of green traffic lights. We always like those. It means that things are built correctly. Now we're looking at the nozzle, so we need to get a mesh in there as well. So this one, much smaller mesh we're going to use. We're going all the way down 5 millimeters because the detail within that bit of the model is much finer. Now we've got the final bit, which is the support for that. Whiz through, we've got a couple of components that have already got meshes created on them. The rest of it, we're going to apply another mesh. I think it's 5 or 15 that we do here. So we're helping the system to create the simulation and run the simulation by not making too fine a mesh where we don't need it, and where we do need it, really making a nice fine mesh. So we've also got a couple of connectors we can see here. So we're going to exclude those from the simulation because we can make those as virtual components, and it'll just be that little bit easier. And we know that that virtual component, like we used in that first resin simulation, are just as functional. So then we run the system and say, right, mesh away. So on 15 seconds. Some assemblies obviously take longer than others. We've got some nice geometric forms here. So there we go. We've got a fully meshed model and ready to be able to do some simulations on. So we've already got gravity set to on here. So that's what we're going to consider. And now we're going to go through the assembly and say which parts within that assembly actually contribute towards the results that we want. Now, we pretty much just want to say, right, anything that's in here is in the real world, and we want it to be considered in our first just static load test. So we whiz through, we do all of that. So here we are, just say that all of these contribute towards the results. All there. There we go. So now everything within this assembly is playing a part. And there we go. So we've got a static load assembly set up. We've got gravity on, as I say. So what this is going to end up looking at is just this as an assembled component for the larger machine. Can it support its own weight in, again, simplifying things? So we'll run the simulation exactly the same way. We've got a choice of running it on our desktop or in the cloud. We've got anywhere between 8 and 144 cores. You could run it on less than 8.
Andy,
you've got free.
8 is out the box, is it?
8 is out the box. You've got 8. So you could run it on 6 or 2 or what have you. But yeah, you've got 8, so you might as well use them. We've run that in the cloud. Going, yeah. So as it's running up in the cloud, you get this feedback, so you can see what's going on, understand that it's running, and see its progress. Now, we've shown a lot of simulation as we've gone across here, lots of clever things. Now, it may be that some of the points that we've raised here are beyond you right now. This may not be a resource that you've got internally. That doesn't mean that you can't do this. Technia have got a team of very clever simulation people that we've mentioned to you before. We can help you get along the road towards a mod sim philosophy. You can see here that we're just stepping through to see how that load of all the various components is put into into the assembly. And so yeah, coming back, we can help you with all of this. We can help you create a workflow to do a simulation. We can help you by running that simulation for you, or we can do a knowledge transfer. So there's a whole host of ways that you can embrace that mod sim, not just by buying the software and hoping that you can use it. So we've got some results there. We want to see how the model supports its own weight. So we're going to look at the von Mises stress plot, and is it stiff enough to hold itself up? And we're also going to look at the displacement plot of that the nozzle jet. Is it staying within those accuracy tolerances that we wanted to make sure that we did at the beginning? So there we go. We see that it makes sense, I guess, doesn't it, Barry? That
Yeah,
we've got the nozzle trying to bend that central bar. We've got the bars bending a little bit to come down, and then we've got a whole host of different ways of displaying this information. So we can see that.
So you can see the nozzle from the bed, kind of, what was it, 0.002.
0.002 of an inch. So that'll be 0.1 of a millimeter or something like that, won't it? In that kind of realm. So, but we can see that that's the most movement of everything. But so what we can do, we can probe it. We'll set up a few probes on this part. We've got one there, another there, and another there. And then we can take this data and put it into an XY plot. So we put a U translation on that and pull through the magnitude. So there we go. Each one of those lines is one of the probes that we were just applying there. We can see that over time the displacement, which makes sense, is increasing. And we can interact with this graph. It's not just that it's driven by the view. We can go the other way around, and we can drive the view by the graph, and we're just dragging along here. So if there was a specific point we wanted to pay particular attention to, we could just click it on the graph, and then it would show us that.
So coming back to your taste test, Andy, we can at any point examine that and say, you know, that's just its normal load there. If we apply water or pressure to that, you know, are you happy that it's going to perform as we think? So you're constantly testing it as you go. Back to the taste test with the chef,
yeah, and then coming all the way back to the I think it was the resume where we were. You could set these up as KPIs, and we can start monitoring them and making sure that things are going the right way. But exactly like you say, it's just us reassuring ourselves that what we're doing is working, and how quickly our confidence level can grow with that. So quick physics lessons for everybody. Apologies if this is something you already know. We're going to start looking at low and high frequency. I know as I've gone through physics and engineering, this has always been something that has bent my mind somewhat. So the way that different parts and assemblies respond to resonance and frequency, it can really be quite disastrous. Examples like, I think it was the Millennium Bridge in London, where everybody started walking at the same pace, and the bridge started swinging.
I remember seeing a video, Andy, years ago from I think it was a Chinook helicopter that literally ripped itself apart.
Yeah, and exactly the same, and that's just what we're seeing here, but with pretty pictures. That as something vibrates, a frequency goes through it, and they can either be amplified or not, depending on how those waves all hit each other. And that's what happened on the bridge, and it's what happened with the Chinook. So we could watch this forever, and some of the views get really quite pretty in it, but we get the idea that vibration can be bad for assemblies.
So that allows us to test to see, you know, do we put any dampening, any components in for putting dampers in and stuff like that? Yeah.
Yeah, but then at the same time, coming back to that test that we'd just done before this, if we put dampening in it, that's going to be something that's soft, which allows movement. So what effect is that going to have on that resting state? Is that dampening that we're putting into this going to mean that the nozzle is going to move more because the assembly has got more flexibility in it? So this is where we can experiment and start figuring out where that balance of vibration versus rigidity comes in. So we've got two parts of this assembly that are going to create frequencies and vibration. The first is this big pump. This is the water coming from the inlet and being forced up to the nozzle. And then we've got the nozzle itself, where it's spewing out the water at high pressure, which has got a frequency to it from the water coming through, but then also applies, going back to basic physics again, an equal and opposite force going up as it's pushing itself out. So the pump,
it's gonna force down a massive kind of load on the steel.
Yeah, but then because it's forcing the water out, it's also pushing itself up, which is all going to exert force.
So that bar across the middle, we think might rotate or bend out of shape, and the brackets it's holding them, they're going to deform, aren't they?
Exactly. Yeah. It's just how much. So we've got a low frequency coming from the pump, and we've got high frequency coming out of the nozzle. So the pump is going to be rotating between 500 and 1500 RPM, and it's going to have a base excitation of 0.01 millimeters. So we're going to have a frequency between 8 and a bit and 45 and a bit hertz coming from that. Now we've got the excitation load of 20 pounds, which I think, what's that? So it's about 10 kilos coming out of, going back up the nozzle for the water, and a frequency of 1500 hertz. So very different frequency states there that we've got going on. Now, just for good measure, we're going to assume that there's a dampening ratio within the assembly of 5%. Now, it's always safer to do this so we get a more realistic result, just assuming that things aren't absolutely rigid, so they're not going to pass all of that that vibration through. So it just helps us get a more realistic result. So a bit of a lengthy video, this one, but now we need to create those analysis cases. So first one we're going to do is the low frequency, and we need to fix. Oh no, sorry. We create the frequency step with a maximum frequency of 1500 hertz. We apply the restraints, so effectively we're just bolting this this entire assembly to the machine that it's within, and we're going to do that with the holes through those feet there.
So clamping that down,
clamping that down, so then it moves with whatever it is. We set up some restraints on the servo motors that move along these extrusions. So we're going for X in that one. We did Y in the other, I think it was, or Z.
Z, going down,
And then we set up the harmonics as well. So we set up the lower hertz and the upper hertz, 1 through 500.
Again, Andy, just coming back to that, how many times before, have you done this where you just kind of assumed something, made it, ran it till it falls apart and breaks itself?
Well,
if you can test this here, you can be significantly more armed to go to, you know, that final production meeting to say, we've done all the tests. Here's the results. Because at the end of the day, we don't know what the customer's going to buy, what they're going to cut on that machine, do we?
No, we don't. And as we'll get to something very similar to that when we start looking at the results. That this is giving us the ability to test in a really broad range, stuff that may not necessarily be the typical work case. So we're setting up the second study here where we're doing the nozzle, but yeah, we don't know what people are going to use them for. Oversimplifying and coming back to the food analogy again, when people design a table, they don't design it just strong enough to hold a plate and the food that's on it. We need to consider the real world of what is actually going to be used this for.
I remember a customer years ago, they used to make staging stuff for the theatres.
Mhm.
And I said, do you ever get concerned, you know, with your kit that you build, you ship to the site, erect it, you know, in the theatre? And they started laughing. He said one show that they made the equipment for, they were told in the brief that this ladder, scissor stack, had to lift up a ballerina onto the stage. And he said, we got tickets to go and watch the show. He said, we're sat there, and all of a sudden, you know, the stage opened perfectly. He goes, the scissor lift then came up through the stage. He goes, there was 8 massive opera singers standing there, big burly men. And he goes, we'd only had it. We only expect it to be a really thin ballerina, not 8 massive guys. So yeah,
And sorry, go on.
So not carry up.
Well, I was going to say, so yeah, just understanding what those limits are, maybe that has gone way beyond what your use case is, and us understanding that and taking it beyond to understand where those real weight limits are, where the limits of this product do come. And it may be something as straightforward as us being able to stipulate working cases. Do not overload by more than X, because it will fail. And all of that, we just, unless we made a whole host of these machines and started testing them to destruction in various different ways, we're not going to know all of that stuff. And we can do umpteen tests within the software to understand where the limits are. And again, come back to, are we over engineering it? Is it engineered enough? It works both ways. So we're still setting up a whole host of simulations here. We've got the low frequency built now. We're just putting in the high frequency as well, and we put the loads in. So this is where we put the force of the nozzle coming, forcing the water out, and like I said, about 88.9 newtons going up, so about 10 kilos. Putting the frequency and how it all works, and add the damping that we were discussing earlier. And then we need to make sure that we get some results out of this simulation. We pick all the various parts that we want to see. The more of these we tick, the bigger the data set is that we're going to end up getting returned from the cloud. Just something to consider. And then again, like we've done previously, run the simulations. 36 cores again, and then we'll run them all concurrently. Away it goes. So we won't sit and watch that run. We'll skip to the next slide, I think. Well, so after a period of time, a few minutes, I think it not typically take for that one, we're going to get some results back. So what are they going to say? We're going to be able to look at the displacement plots and see if there's any excessive deformation, which is going to, again, maybe make that WaterJet wander and stop making accurate cuts. We're going to be looking at the coupling response and any displacements on the accelerations on the tooltip, and then we'll be able to compare the results from both the high and the low frequency resonance. So here we are. We can see that the low frequency has quite a varied effect on that tooltip, depending on what frequency we're at. As we're moving through these frequencies, different parts are moving, and that's because each of them have got their own frequency that they respond to. But overall, as we look at the load and displacement, we can see that the displacement is 0.001 of a millimeter, which is well within the regions of our performance requirements. So we're happy enough with that. But what we can also see is that at certain frequencies, we are getting some amplification, and these could be something that we need to consider. Now, typically these aren't in the normal working range of the product, but maybe, again, like Barry was saying, we told people that this is for cutting steel and aluminium, and they've all of a sudden decided that they're going to cut titanium with it, and in order to cut titanium, they take the machine out of its working range, and then it breaks, but we don't know why. And without running these simulations, that pump in standard working form wouldn't get to the point where it would break like that. But this allows us to visualize and to test scenarios which maybe are out of that normal working environment, but need to be considered to make sure that the product is safe. So now we're looking at the high frequencies.
Yeah.
And a nice little way of visualizing, I think, there, of just being able to see where that deformation and the movement
through that as well.
Yeah. So we can see, and depending on what frequency we've got, we can see where the movement is. They're all exaggerated. Hopefully people had assumed that already, but these vibrations don't make this this assembly look like it's been made out of putty. So we can see that generally this would the working fine on that area. So again, being able to scrub through on the graphs rather than having to drive everything from the assembly interface. Does it stop there? Is it?
It does, yeah.
Because I clicked. Whenever I click, it stops.
There's a simple answer to that, Andy.
I won't tell you why I was clicking, but so now, like we did in the bushing, most effectively, we can pull all of this information into our results viewer, and that allows us to view both the low and high frequency studies at the same time. Allows us to move through the graphs and just see, oh, okay, so if we were looking at this low frequency and that high frequency together, where are we going to be? Just a very good way of doing a design review and understanding what we're looking at. So, and we've done all of our analysis there. So let's round off by looking at what we did. So we created the meshing. We did a static analysis to see how this assembly supports its own weight. Considered gravity in that. We did a low frequency analysis so we could understand the forces that the pump were putting onto the assembly, and we did a high frequency analysis so we could understand the pressures and the frequencies that were coming from the tip of the nozzle, which is doing the cutting. So although we kind of whizzed through it there, we did an awful lot of analysis on that assembly, and now all that hard work's done.
I would be comfortable going into a production meeting on a Friday and having the old QA guy in the corner of the room go, "This won't work." Yes, it will. We've tested it. It's here. I'm
Yeah.
confident. I'm comfortable.
Yeah, absolutely. Well, we've covered a lot of bases there. It's very thorough, and we can then do what ifs. If we made that thicker, if we made the pump more powerful, if we made the pump less powerful, we can explore a whole host of different ideas. So again, rounding off by the backbone to all of this, we've looked at, we've taken data from SolidWorks, we've worked with it in Simulia, but we're using the 3DEXPERIENCE platform to pull all this together. It's allowing us to design together, to simulate together, and then collaborate. So all of the different departments are able to put their input into the project. So we can see here that we've got the 3D Play dashboard so that people can have a look at the assembly and can put feedback in there. And these aren't SolidWorks or CATIA users. These are just people with input and stakeholders in the project. It's where we can request that we do some simulation work and try and understand what's going on.
Yeah. So again, true collaboration there. You know, having the red line in the viewing marking up and stuff. That to me is an amazing bit of kit, that one, Andy. For, you know, minimizing the time on a Friday, sitting there listening to somebody moan about what you have done, what you haven't done. It's all they can see live what's happening to that particular product, the design.
Yes,
it's gone from being a concept to kind of, you know, you are way further down the process, adding, you know, more and more people into that process as you go.
yeah, and this isn't just limited to a desktop computer or a laptop. You can access the 3DEXPERIENCE platform from a tablet, from a phone, and do everything that you can see here that we're covering in this little bit of the video. Even rotating the models and viewing the simulation study results. So all of this information, rather than just being held in the design department, now everybody who's got some form of input or concern with it has got access to it so that they can start understanding. So you can see there that there is another study that that can be done on this assembly. If anybody wants to see us do some motion analysis, understanding how things, how the acceleration and backlash are concerns in this part, then do get in touch, and we'd be more than happy to do an extra little session for people who would like to see that. But then again, looking at the results and being able to put feedback into them. So this may be somebody sat on a train or a plane, just got 10 minutes and wanting to just give their 2 penneth of an opinion into this. So
yeah, like it.
I think this just goes on showing a little bit more of that interaction as we go on, even through to just looking at the results and what have you. So coming back to the key takeaways, and half of me feels like we just keep repeating all of these the same for every demonstration that we've given, but they are the same. We've come from 3 very different disciplines. We've done 3 very different simulations, but all of them have been using the same technology in the background and are providing
and follows that mod-sim approach of kind of, you know, what you stress in the video: taste it early, test early, get it right.
Yeah.
So simulate as you design.
Yeah, and we with that, we're improving quality, we're accelerating innovation, we're taking away that fear of innovation, and that's when you really start making some special ideas. And for the business, again, all of those the benefits are the same. Again, we're reducing our IT costs, but increasing innovation. We're getting a better idea of warranty and reducing warranty costs, and we're becoming that brand that people look to for the most innovative and high performing products. So that's your three. We've looked at the resin, we've looked at the dolly for the train, and now we've looked at the assembly for the WaterJet cutter. All of these are things that have had similar implementations within Technia. If there's anything that's kind of sparked a thought or made you think maybe we could do this, or feel free to get in touch with either myself or Barry. We'll do our best to help you with any questions. We can help you with software, we can help you with process development, we can do that engineering and process development in-house at Technia, or we can just help you get your set up. So yeah, don't be shy at coming forward. We'll be more than happy to help you however we